L'Hopital's rule is a method for evaluating limits using derivatives. We typically apply this rule when running into an indeterminate form. An indeterminate form is a numeric expression with no clear value associated with it. There are 7 in total, but I've classified them into the following categories. The first being the rational, the second being the exponential, the third being the difference, and the fourth being the product. In this lecture, we'll be going over how to apply L'Hopital's rule for each of the following cases. So here's the first example. Here we have the limit as x approaches infinity of x squared over e to the x. The first thing that we need to do before applying L'Hopital's rule is to do a direct substitution. This step is very important, as if we don't get an indeterminate form from this, we cannot apply L'Hopital's rule. So let's do that right now. As we can see, I'm going to plug in infinity to x squared. When I do that, I get infinity squared. I'm going to plug in infinity to e to the x. When I do that, I get e to the infinity. Simplifying this expression, we get the following. Infinity squared is just going to be infinity, and e to the infinity is just going to be infinity. So as you can see, we have an indeterminate form, and therefore we can apply L'Hopital's rule. So L'Hopital's rule goes by the following. When we get an indeterminate form, what we can do is take the derivative of the top function and then the derivative of the bottom function, and then apply another direct substitution. So let's do that right now. As you can see, we have the limit as x approaches infinity. The derivative of x squared is just going to be 2x, and the derivative of e to the x is just going to be e to the x. Plugging in infinity, we get the following. We get 2 multiplied by infinity over e to the infinity, which can be simplified to just infinity over infinity. So as you see here, we get another indeterminate form. If this happens, you can actually apply L'Hopital's rule again until you get your answer. So let's do it again. The derivative of 2x is just going to be 2, and the derivative of e to the x is just going to be e to the x. Plugging in infinity, we get the following, 2 over e to the infinity, and 2 over e to the infinity is just going to be 0. So this is our answer, and that is the first problem done. So here's the second question. It tells us to find the limit as x approaches infinity of x multiplied by sine of 1 over x. The first step that we need to do, obviously, is do a direct substitution to see whether or not we get an indeterminate form. So let's do that right now. What I'm going to do is I'm going to be plugging in infinity into the places where x's are at. So when I do this, I should get infinity multiplied by sine of 1 over infinity. Now, I'm going to focus on the sine of 1 over infinity part. 1 over infinity can be simplified to just 0. So we're going to do the following. So it's going to be infinity multiplied by sine of 0. Sine of 0 can be evaluated to just 0, so we have the following. Infinity times 0 is the indeterminate form that we get from a direct substitution. Therefore, we're given the first green light to start L'Hopital's rule. So in the case where we have two functions being multiplied together, what we want to do is we want to rewrite this so that when we do another direct substitution, we get a rational indeterminate form. So there are one or two ways that you can do it. You can either keep sine of 1 over x stationary and then divide that by the reciprocal of x. So for example, we would have sine of 1 over x divided by just 1 over x. Or you could do the opposite and keep x stationary and divide that by 1 over sine of 1 over x. The general rule for this is that we want to have the simpler function be the denominator and the complicated function be the numerator. So in this case, I'm going to keep sine stationary. So when rewriting this limit, we're going to have the following. We're going to have the limit as x approaches infinity of sine of 1 over x divided by 1 over x. If we plug in infinity by a direct substitution, we get sine of 1 over infinity times 1 over infinity. 1 over infinity is just going to be 0, so we have sine of 0 over 0, which is just 0 over 0. So now that we have that rational indeterminate form, we can apply L'Hopital's rule. So the derivative of sine of 1 over x is just going to be the following. We have negative 1 over x squared times cosine of 1 over x. And if you're wondering how I got that, I just apply the chain rule. Next, let's do the denominator. The derivative of 1 over x is just going to be negative 1 over x squared. If you're wondering how I got this, 1 over x can be the equivalent of x to the negative 1 power, and then I just applied the power rule from there. So once we have that, we can clearly see that we can cancel out the negative 1 over x squared from both the numerator and the denominator, leaving us with the following limit expression. Cosine of 1 over x. Plugging in infinity into our function right here, we get cosine of 1 over infinity, which can be rewritten as cosine of 0, which can then be rewritten as 1. So this is going to be our answer. And that is it for example 2.